Day 64 notes, Algebra 2. Today I'd like to review some of the work that we did last week and also extend the due date for the homework that was due Friday of last week. I'll go ahead and give you an extra day to work on that, and you can spend the rest of the class period today working on it, following the notes and examples from this video. Also, after watching the video and completing these examples, I'll give you an opportunity to maybe repair some of the work that you did on the quiz from last Friday as well. So what I'll do in this video is pick a couple problems from Math Excel and work through them here and show you my approach to them. And you can use the same approach or you can modify it as necessary until you find a procedure that works well for you. And then towards the end of the video, I'll show you a new technique where we can use technology to help us do some similar exercises. So here we go with number 1. On this Math Excel assignment, I know it's really small, hopefully you can read it. It reads that f of x is equal to x cubed plus 7x squared minus 49x minus 55. Our job is to find the real zeros of f and also to use the real zeros to factor f. So the first thing that I'll probably do here is write the problem down and identify my p and q values so that I can utilize the rational roots theorem. Here's the equation written. Now, in this case, p is equal to 55 and q is equal to 1. Now, the factors of p are 1, positive and negative, and it's 1 times 55. That would equal 55. So I know 55 is the biggest factor. Then I have a positive and negative 5, which multiplies by a positive and a negative 11. And those are all the factors of my 55. Fortunately, since our leading coefficient is a 1, the only factors of 1 are positive and negative 1. This is going to make utilizing the rational roots theorem a little bit easier. With both of those sets of factors identified, we can identify possible roots, so possible rational roots. Now, this won't find all real roots, but it could list all of our rational roots here. Possible rational roots exist at all of the factors of p divided by all of the factors of q. And so in this case, if I were to divide 1 by 1, 5 by 1, 11 by 1, or 55 by 1, well, all of the results are pretty easy to find. It's either going to be a positive, negative 1, 5, 11, or 55. So we have 8 numbers to investigate at this point, and investigating 8 numbers is a heck of a lot better than trying to guess at random any number that could possibly divide this function. So let's go ahead and make up a list and start working through it. We need f of 1, f of negative 1, f of 5, f of negative 5. We need f evaluated at 11, negative 11, 55, and negative 55. Now, once I find one root, I'm actually going to stop searching for the others because I notice that this is a cubic polynomial. And if I can factor out one root, then it's going to reduce this from a cubic polynomial into a quadratic polynomial. And quadratics, we have many different ways to find solutions. So again, if I can turn this into a quadratic, I would rather do that and then find the solutions using the methods that we've practiced in other units, rather than looking for the results from the rational roots theorem. And that's what this reminder is here for. It says once a root is found, divide its factor from the original polynomial, and then hopefully you've got something that you can work with. So I'm going to go to the TI calculator now and enter this equation with perhaps the letter a in place of x. I recommend that you do the same. Go ahead and pause the video now and set up the calculator. Okay, and this is what it looks like in the calculator the first time. Again, we're using the letter A in place of X here. And the calculator doesn't understand what the value of A is supposed to be, so we have to store a number in its place. So I'll type the number 1, press the Control Variable button to pull up this storage command. We're going to take the number 1 and store it in place of A and press Enter. Now we can jump up to our previous entry, press Enter again, one more time, and we see the result. When A is equal to 1, our end result is negative 96, not a 0. So let's check the next one. And sure enough, when A is equal to negative 1, we get a 0. So I'm going to stop here at this point and now use synthetic division to break down the original polynomial. And with synthetic division, I'll just use the coefficients. So I need the coefficient of 1, positive 7, negative 49, and negative 55. And I'll set up this L chart. Now my 0 is located at negative 1, so I'll use negative 1 here. Don't use a positive 1, okay? Don't use a positive 1 here. We only need to change the signs if we're going from a factor when it's written in binomial form. So for example, when the 0 is at negative 1, the factor would have looked like a positive 1, x plus 1. And so if we go from this positive 1 binomial, we change its sign. But if we have the 0 written in this function form, we don't need to change that sign. Hopefully I didn't confuse you with those side remarks. If I did, just ignore that. Again, we're just using the number that we found the 0 at here in our synthetic division. So to complete the synthetic division, I'll bring this 1 straight down, then start multiplying negative 1 times positive 1. Add these two together, multiply. Add these two together, multiply, and add these two together. We see our remainder is 0. So what this has done for us is it's changed the form of the polynomial. The original polynomial can now be rewritten as x plus 1. Again, this is the factor that came from this division here. And what we're left with is the polynomial that came from our division, x squared, x minus 55. So we have x squared plus 6x minus 55. And again, since this is a quadratic function right here, a quadratic polynomial, chances are we can factor it, or if we can't factor it, we can at least use the quadratic formula to solve it. And so that's what I'm going to use here. Actually, no, I think we can factor this. Two numbers that multiply to equal negative 55 but add or subtract to equal positive 6, well, those exist. We have an x with an 11 and a 5. If I use a positive 11 and a negative 5, those two multiply together to equal negative 55, but add together to equal positive 6. So this is the factored form of the polynomial. So this is actually a good answer for part B, when the problem asked for us to, oops, it's not on this page. When the problem asked us to factor f, this is a good solution for that. Now, as far as our zeros go, we need to list those separately. The zeros in this case exist at negative 1, first off, because that's what we found here, and that's what we used in our synthetic division. That's what came from this factor. Then the number negative 11 comes from the next factor, and then the number positive 5 comes from the final factor. And this would be what Math Excel is looking for in part A, the numbers -1, -11, and 5. Now, I don't think Math Excel is picky about the way we write our numbers. I might encourage you to write them in numerical order so that we write -11 first, then -1, then +5. That's more of the traditional way that we would write our solutions. So I'm going to zoom out just a little bit here, and you can see all of the work that went into this. It's not an awful lot of work, but there are distinct pockets of work that we had to complete. Let me see if I can review this with you. We wrote down the original polynomial. We found the factors of the p and the q values, and then listed our possible rational roots. From here, we started checking those rational roots using the remainder theorem. And once we found one root, we didn't bother checking any of the others, because we then used synthetic division to reduce this from a cubic equation down to a quadratic equation. And with the quadratic, I should say polynomial, it was easy to factor at that point. And each of these three factors produced 3 real zeros. Allow me to demonstrate another problem, perhaps slightly more difficult than the first. Okay, so this one comes from number 7. I think it's probably one of the more difficult problems in the homework assignment. It's a quartic equation. It's got a leading coefficient that's not equal to 1, and the trailing coefficient, or I'm sorry, this constant here at the end has a lot of factors to it. So let's just get started with this. Here's the equation, and the first thing that I'd like to do is identify the p and q values. So in this case, p is 56 and q is equal to 2. Now the possible factors of q are positive and -1 and positive and -2, and that's it for q. As far as p goes, there are several more. We've got positive -1, positive and -56. How about a positive -2, and half of 56 is 28, so positive -28. 56 can be divided by 4, and that is 4 and 14. So those are the possible roots there. And then finally, positive -7 and 8. Those are the last factors that could divide 56. Now, the real trick becomes what to do next. Every factor of p needs to divide by every factor of q. So we've got a lot of these numbers that we can start checking. Again, every item in this group can be divided by 1 to list a possible factor, and then every item in this group can be divided by 2 to list a possible factor. So I'm going to write those here, p over q, and we'll show that list. First off, I know all of these are going to get repeated because when they're divided by 1, the end result's the exact same as those original factors. Now for the next round, I'm looking at, again, each one of these p values, each one of these factors of p divided by the factor number 2 of q. Now, in this first case, 1 divided by 2, that produces a factor of 1/2, 1 divided by 2. 2 divided by 2, though, is 1, and we already have that listed, so I don't need to create a new one for this factor. 4 divided by 2, well, that's 2 again, so I don't need to check it again, so I'll skip that one. But 7 divided by 2, that's a positive and -7/2. That's a root that I should check. 8 divided by 2 is 4. I don't need to check that one. 14 divided by 2, that's 7. I don't need to check that one. Again, those two already showed up in my list before. 28 divided by 2 is 14. That's in my list. And 56 divided by 2 is 28. That's already in my list as well. So really, this just produced two more factors for us to investigate. Now, in the interest of space, I probably won't list all of these like I did the last time. Last time I listed out all of the potential zeros so that I could check them. I'll probably just write them down as I check them, making sure that I do evaluate every option. So the first one I'm going to check is a positive 1, and I need to set up the calculator this time for that function. Okay, and so this is the function. Now, on my calculator, I already had a stored as a -1. So when I press enter here, this would be the result of the function evaluated at -1. So that's a 90. I'm going to go ahead and write that down. F of -1 is 90. So that's not a 0. But if I change it to a positive 1, so let's take positive 1 and store that as a this time. We'll press enter, jump up till we have that equation highlighted, repeat that equation, and now I have a result, and that does equal 0. So that's good. I found at least one 0. Now I can't stop here because my original equation was x to the 4th power. If I only divide that 0, I'm going to reduce it to a cubic function, and I need to get it down to at least a quadratic. So I'm going to keep working until I find another 0. Let's keep working until we find another 0. So I'm going to check f of 2 next. F of 2 and then f of -2. So when I store 2 in place of a, and if I repeat that calculation, oh well, what do you know? We got another 0 there. So that's really, really fortunate for us. We found a 0 that quickly. So I have 2 zeros. That's enough for me to reduce this quartic polynomial into a quadratic polynomial. And let's go ahead and work through that. So my coefficients are 2, 9, -13. So 2, 9, -13, -54, and +55. With those coefficients, I am going to divide by the 0 at x equals 1 first. So let's go ahead and do this. We'll bring the 2 down, multiply, add, multiply, add those two, multiply again, add them, and multiply. Oops, I think I wrote this down wrong. This was a 56 from the beginning. Yeah, 56. Okay, good. Now these two add to make a 0, which is what we expected. We expected to have a remainder of 0. Now that shows the result from the synthetic division when I use x equal to 1. Without stopping, I'm going to divide this now by x equal to 2. So I'm going to factor out this next factor immediately. So let's use synthetic division to do that again. We'll bring down the 2 and multiply, add those together, multiply, add those together, and multiply. Oops, I got my signs mixed up here. -2 plus 30 is a positive 28. This should be a positive 56. That's what I get for trying to rush through this. And those two add to equal 0. And so what we're left with here, and actually what we were left with after each division, was a polynomial that had 1 degree less than the one prior to it. So this result was a polynomial to the 3rd degree. And this is now a polynomial to the 2nd degree, 2x squared plus 15x plus 28. And so the original polynomial, f of x, could now be written partially factored with an x minus 1 and an x minus 2. Those two factors come from these two zeros that we found originally. And we have this 2x squared plus 15x plus 28. And what we would like to do at this point is try factoring this, or at least finding the result to that quadratic expression. We could use the quadratic formula, but I have a hunch that this can be factored. So I'm going to split the middle. I'm just going to jump over here and split the middle. 2x squared times 28 is 56x squared. So that's going to go in the top of my x, and in the bottom of my x, I'm going to write 15x. And two numbers that multiply to equal 56 but add or subtract to equal 15, that sounds like 7x and 8x to me. So I think we can rewrite this function again. I'll leave x minus 1 and x minus 2 alone, but at least this polynomial in the center can be rewritten now as a 2x squared plus 7x plus 8x plus 28, and now we can factor by grouping and see what we get. So again, f of x equals x minus 1 times x minus 2. Our GCF here is simply an x. Now we have 2x plus 7. Our GCF here looks to be a 4, positive 4. That leaves us with a 2x plus 7, and which is good because these two match. We can keep moving forward. F of x is then equal to, again, x minus 1 times x minus 2 times x plus 4 times 2x plus 7. So we have the solution to b now. This is our factored form of the polynomial, and because of the factored form of the polynomial, we now have solutions for x itself. This identifies where our zeros exist. The smallest zero exists here at -4, so I'm going to list it first. Then the next zero comes from this one. If I were to set this equal to 0, 2x plus 7 equals 0, I'd subtract 7 and then divide by 2, and x would be equal to -7/2. That's about -3.5, so that's why I would write it next. And then from there we have a +1 and a +2. And that's the order that I would write my solution in for part A. So I'm not sure where the hang-up was last week. I think a few of us may not have recognized that we could have repeated our synthetic division. Maybe a few of us got a little bit lost when we were identifying the potential rational zeros using the rational roots theorem. But again, hopefully these two examples will help you make corrections and accurately finish the homework from that was originally due Friday. Now feel free to go back and pause the video at any time, look at these notes, and use them as a guide while working on homework from Math Excel. I'm actually going to create a second video since this one's getting so long. I'm going to create a second video that helps us identify another way that we can use technology to solve problems very similar to this.